Let's talk about a special type of function known as a sequence. So in mathematics, a sequence is one of the most powerful tools that you have in your kit. Probably more powerful than you realize, because what you find is that a lot of concepts can be represented in terms of a sequence of points. So mathematically what we do is we define some function. We say, all right, I have a function and the domain is positive integers. Now we're used to thinking of functions having domains that are like intervals or some sort of other continuous, or a union of continuous blocks. But in this particular case we only have, a lot of times only is the positive integers, but sequences can have more than that. So that means that it's evaluated at 1, at 2, at 3, at 4, but it's not evaluated at 2.5 or pi or anything like that. It's just evaluated at 1, 2, 3. And if we take a look at the function outputs there, we can kind of think of them as like a list, right? We have a term that starts at 1, at 2, at 3, at 4, at 5, at 6. And we kind of write those terms as like the first term. If the sequence has like what's called an A, we'll say it's the A1, A2, A3. Or we might say the first term, the second term, the third term. And then we go out to what's called the nth term. And when we think about a sequence, describing the nth term is really important, because if we can describe an nth term, we're usually saying, I'm going to describe an arbitrary term. I'm going to define a function like f of n, that when I plug in n, I get the sequence term out. Really good examples of this would be in pattern recognition. What you say is you have a sequence of values that have come in, and you're trying to figure out what is the pattern along those sequence of values. Can we say that when a person is betting, that they would bet this exact amount on their 5th bet? Or when they do something, how can we describe that? How is that different from their 6th one? Can we find patterns in the data? And that is the essence of what sequences are. They're really these ideas, this stream of information, and we're looking for a pattern. Now, that's not always easy to do. It's not always practical. In many cases, it's not really possible, though you can get close. But in the case of what we're dealing with here, it's going to be possible for most cases. Anyway, but the idea is that they have a domain as an integer. But the thing about the domain being an integer is that integers don't stop, right? If I start at 1 and keep going, it eventually goes all the way out. So a lot of times it's also helpful to figure out if a sequence, what the sort of infinite term is, like what happens when the sequence goes to infinity. The reason for this meaning that if you have a sequence that's maybe you're taking sample values on a system, like a machine, and you have a sensor, and that sensor updates let's just say every half of a second, right? Then you can think of that, or maybe it's every 1 second for our case here. If it's every 1 second, you have the first update, second update, third update, fourth update. And if we start to notice there's a pattern in those updates, we can say, okay, run this thing out to infinity and see if it stays bounded. See if it essentially blows apart, or if we can have some idea of how the behavior is going to be as we go out to infinity. And that's going to be important to examine, not only for real-world applications, but specifically mathematics, the idea of thinking about things mathematically, combining the idea of limits and these, what we call discrete values, has a surprising amount of usage and powerfulness that we'll get to as we go on through all these sections. So again, we want to take that limit. Now, I've kind of talked at a high level here, but I want to talk about some actual sequences, some simplistic examples, and we'll do more examples in an example video, but I want to talk a little bit now. So if I have some sort of sequence, and a lot of times it's written as a set because it's a set of terms, and each term is 3 plus 1 over n. Well, then if I look at that sequence, the first term is 3 plus 1 over 1, because that 1 here, see the n matches the n, so the 1 matches the 1. Well, 3 plus 1 is 4, obviously. In the second term, we have 3 plus 1 over 2, right? So those terms match. 3 plus 1 over 3. Now you might ask yourself, okay, what happens as we take this sequence out to infinity? Well, let's think. As this number gets really large, so does that number. And then 1 over a really large number is just, it shrinks to 0. So what we can see is that that sequence, as we plot it, becomes just 3. It becomes infinitely close to 3. So we say the limit of that sequence is 3. Now, this one's a little more complicated. N over 1 minus 2n. So our nth term, so n, n, n. So every time you update this number, you update these two numbers. So in the first case, we update those two numbers, and we get -1. In the second, for the second term, we update those two numbers. We get -2/3. For the third term, we update these two numbers, and we get -3/5. Now you might ask yourself, okay, how do I get the limit of this sequence? How do I take n to infinity? Well, what you find is that you have to be a little bit careful. You have to be a little bit careful because this doesn't always work. But what you can do is take like the limit of the continuous function, right? If this was f of n equals this over the entire real numbers, not just the integers, over the entire real numbers, or at least the positive real numbers, you can usually take that limit, and if that limit is 0, then the whole thing's going to be 0, which is nice. But if that limit's not 0, you do have to be a little more careful, and we'll get with sequences like that as we go on, so don't worry about this now. But if I were to take the limit as n goes to infinity here, well, it would just be kind of an infinity over a negative infinity. So then we could take L'Hopital's rule, and it would then be the limit of 1 over -2. So we would get -1/2. And if you think about that, that kind of makes sense here. We have -1, it shrinks a little bit. This number on top is still, it's not quite 1/2, it's a little larger than 1/2. That's a little larger than 1/2. The next one would be 4/7, and then you would end up with, or -4/7, and then you would end up with like -5/9, I guess, -5/9. And what you see is that the bottom one keeps skipping 2. See, it's like -1 over 1, 3, 5, 7, 9. They keep skipping by 2, and the top one keeps skipping by 1. So overall, those terms dominate, and you end up with a -1/2. So that's kind of an interesting idea as well. Now, there's another type of sequence I do want to talk about, and this is the idea of a recursive sequence. So when we think about sequences, it's really nice when they're written in what's called a closed form, where it just says the 5th term is 3 plus 1 over 5, right? The nth term is 3 plus 1 over n. That's easy. It's essentially just a direct evaluatable function. But recursive sequences are something you may not have seen before because they don't really make sense for continuous functions, but they make sense for these discrete functions. So what we say is, look, I know the first term. I know that the first term is 25. And all I know is that each term is 5 less than the previous one. So I say, okay, each term is the previous one minus 5. See that sort of notation? It's dn plus 1. So for instance, if this is d3, then this is d2 because this is one more than that one. So d3 is equal to d2 minus 5. So what I'm saying is I've noticed a pattern. I noticed that each one is 5 less, so it keeps going down by 5. And if I run this with that definition, I get my first term is 25, that's already given. My second term is the first term minus 5. Well, that's 20. The third term is the second term minus 5. That's 15. And so on and so forth. And obviously, as you went to infinity, this thing would just shoot down to negative infinity. But one thing that's helpful when you have a recursive sequence, and this is not always possible, but it is very, very useful if you can do it, is instead of having this definition is cumbersome, because if I wanted to get the 1000th term, well, I know that the 1000th term is the 999th term minus 5. But I don't know the 999th term, so I got to figure out what the 998 term is, and the 997 term, and the 996 term. And you can see where that causes a lot of problems, because to get to this point, I have to compute every point in the sequence before that. And that's really, really, really difficult and frustrating. So it's nice if we can write this in the closed form. And that's this idea. You say, in this particular case, it's the dnth term is 30 minus 5n. You'll notice this matches. D1 is 30 minus 5. Okay. D2 is 30 minus 10. D3 is 30 minus 15, and so on and so forth. And it's a little beyond the scope of what we're talking about right now, proving how I did that. I mean, obviously, you could just say, okay, well, clearly it's true. But mathematically, proving that is a little more complicated. But nonetheless, these are important tips, and sequences are the baseline for everything we're about to do for these next few sections. So take sequences seriously, because if you actually truly understand them and deal with them intuitively, it makes everything else that follows a lot easier to understand.